So there was a question about why the Cauchy stress takes on this apparently curiously limited form for an isotropic material. Okay, for isotropic hyperelastic materials, okay, I stated without proof that sigma has this form. Okay, where the alpha i's are functions of the principal invariance. And the question was, how come if you're doing true nonlinear elasticity, we have, this thing gets truncated at b square. It seems almost like a Taylor series expansion that starts out and for some reason just stops at b square. Okay? And the answer is that, well, one can prove this. Okay? One can prove this, and okay, or properly stated, one can prove, I guess, the correctness of this form or the completeness of this form. Okay? And the steps in the proof are actually what I laid out at the beginning of the last segment. They come from the fact that tau has this form. Okay? And the fact that psi is a hyperelastic strain energy function, that's also for an isotropic material. Okay? Okay? Of course, if it is for hyperelastic material, we already know that we can write it out in this form where now psi depends upon b through a particular function psi hat of b, right? And we've demonstrated that. The other thing you need to recall is that it must also be frame invariant. Okay? What this means is that psi hat of b can be represented, must be representable actually, as, now I forget what kind of decoration we used on this, but I'm going to use psi double tilde here. Okay? The fact that it is isotropic as well as frame invariant means that we've got to be able to write it as a function of the invariance of b. Okay? And therefore, our expression for the Cauchy stress is 1 over j twice derivative with respect to b of now a psi double hat, which depends upon b through its invariance only, through its principal invariance. Okay? Right? And of course, we could also write it the other way, right? With the tensors commuting. Okay? And this step really is the key. Okay? Because what this lets us do is to say, therefore, that sigma is 2 over j. Now, those derivatives of psi double tilde with respect to b can be expanded using the chain rule as this. Okay? And this is the key. Okay, observe that these are just scalars, right? So these functions, whatever these derivatives are, go into the alphas. Okay, they help us start defining the alphas. But then if you recall what the invariants are, the first invariant is the trace. The derivative of the trace with respect to the corresponding tensor is just the isotropic tensor. Okay? This one is a little more involved, but it is essentially this tensor, if I recall correctly, gives us b. Okay, that derivative. Okay, because if you remember, the second principal invariant is trace of b squared minus trace square of b. Okay, so it's quadratic in b, and so a derivative with respect to b gives us something of the order of b. And then this is just the derivative of the determinant with respect to a tensor. Okay, and this is an object we've computed several times during this series of lectures, and it eventually takes on the form B inverse transpose, which is of order B inverse. Okay, and so now you see it, when B multiplies this, you get the isotropic tensor. With this one, you get B squared. With this, you get back B. Okay, so that's the key. All right, so the details can be worked out, but the nice thing is that this is a theorem, right? Because it can be proved for isotropic materials. Surprising, right? But that's another one of the surprises that nonlinear elasticity packs. Okay, all right.